All right, so what's going on, y'all? Let's do 329. It's a plane truss. We have to determine the horizontal and vertical displacements of node 1, which is just U1 and V1, and the stresses in each element. They all have the same EA, and in this case, they're all 3 meters long, same length. So let's go ahead and get started. All right, so this problem's no different than any of the other ones we haven't done, right? We got 3 elements. We got this one, and this one. They all have the same length, same E and same area. So our EA over L is going to be the same for all of them. So we could go ahead and just continue doing the matrix, the table. So again, we're going to assemble each stiffness matrix for each beam. And then obviously using each angle, right? We'll talk about that in a minute. And then just pretty much make the global equation, the global stiffness matrix, using all 3 of these stiffness matrices. So for the first element, we got 3 elements, right? So let's go ahead and make this table. Sorry, let me just go ahead and do the lines, right? We got 3 elements. So we got 1, 2, and 3. Let's go ahead and stick with the first element, right? It's this one up here going straight up. Now again, you determine this angle with respect to the positive x-axis. So you could, this is your positive xy, right? You could go ahead and do it at this node, right? If you do a positive x this way, this angle here is 270. And if you do it this way, you could go ahead and put 270 here, but when you do the stiffness matrix for this specific element, you're going to have U2 V2, U1 V1. Me personally, I do not like to do that. I like to start at the lowest number node, if you've seen the other videos. So in my case, I will start here, and this angle here is a positive 90, right? It's going straight up. So my angle is going to be 90. Again, you could have a 270 if you start it here, but I'm going to go ahead and use 90. Do it right here. So the cosine of 90 is 1, sine of 90 is 0, cosine squared is 1, sine squared is 0, cosine times sine, that's 0, and then we'll do EAL at the end. So for element 2, right, again, I like to start at the lowest node, which is 1, not 3, and I like to work my way to 3. So that angle is 45 degrees. Again, if you wanted to start at 3, your angle would have been 180 plus 45, which is 225, right? So this angle would have been 225, and you would have had U3 V3, U1 V1. But since I chose 45, starting at node 1, I'm gonna have U1 V1, U3 V3. Okay, hope that makes sense. But just FYI, I wanna make sure you understand how you work with the angles. So if you do that, your cosine is radical 2 over 2. Same with sine, right? Cosine squared is 1/2. Sine squared is 1/2. Multiply both of them, you get 1/2. Same thing. And finally, element 3, that's angle 0. Again, I like to take it from here. If you would have done it here, it would have been 180. But continue, right? 0 degrees. It's from 1 to 4, so that's why it's 0. Cosine of 0 is 0. Sine is 1. You got 0 for c squared, and then 1 for s squared, and then cs is 0. And yeah, that's pretty much it. Hold on, give me 1 second. Oh shit, my bad. I am tripping. So these numbers are flipped, right? Cosine of 0 is 1. This right here is going to change. This is going to change. This is going to change. Cosine times sine is 0. My bad, I had them flipped. It's a good thing I caught it. And I noticed it because cosine of 0 is not 0. That's why I was tripping out. I was like, wait a minute. So this is 0. This is 1, 0, 1. And this one's 1, 0, 1, 0. Double check these, but I'm pretty sure this is correct. Cosine of 90 is 0. Sine of 90 is 1. Cosine of 0 is 1. Sine of 0, it is 0. Cosine squared is 0. Cosine squared is 1. Okay, that makes sense. 1, 0, yep, cool. So we're good. My bad. Okay, so finding EA over L now. So it's EA, right? That's 210 times 4. That's like 840. This is a 10 to the 9 right here, that little g. Giga, right? And 10 to the negative 4, that's 10 to the 5th. So 840 times 10 to the 5th divided by 3. That's going to give you 280 times 10 to the 5th Newton per meter. And same for all of them, right? So go ahead and fill that in. And it's good when they share the same EA over L, because that means you could add the matrices together without having to alter them in any way or whatever. So this is step 2, right? Doing I call them the little matrices. It's going to be K1, first element, is equal to EA over L, 280 times 10 to the 5th. Now we're going to do the matrix. So it's U1 goes from 1 to 2, right? So it's U1, V1, U2, V2. And then we got U1, V1, U2, and V2. Cool, so close that bracket. All right. Just fill it in, right? So you got the cosine squared, sine squared, and cosine sine. Plug them into this matrix. So it's cosine squared, sine squared, cosine squared, sine squared. So for the first element, it's going to be 0, 1, 0, 1. So that is 0, 1, 0, 1. Next one is CS, negative CS, CS. So it's 0 for all of them. So it doesn't matter. Then that's going to be a 0, 2 up there, right? Negative cosine, sine. And then negative c squared, negative s squared. So it's 0, negative 1. And it's symmetrical, right? So these 3 zeros go down here. 0, negative 1. So 0, negative 1. And then finally 0. All right, cool. K2, let's go ahead and do that. So that K2, right, it's between nodes 1 and 3. And again, it's 1 and 3 because that's the angle we determined. Remember, I explained if you would have done the 225, what is that, 180 plus 45, 225, it would have been from U3 to U1, 3 to 1, right? But in this case, we did it from 1 to 3. So it's U1, V1, U3, V3. And cool, just let's continue doing the matrix, right? Let me go ahead and do this here. K of element 2 is equal to 280 times 10 to the 5th. Same EAL. It's not just, well, I'm just not BSing it, right? It's just because they have the same EA over L. Okay, now plug in. So normally I would like to factor out the half to not work with complicated numbers here. But I'm not going to do that because then this is already the same, so I'd rather just keep it whatever, okay? So it's half, half, and half for everything. So it's half, 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 negative half, negative half, negative half, negative half, 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 half. Okay? 1 half, 1 half, 1 half, 1 half, 1 half, negative 1 half, 1 half, negative 1 half, negative 1 half, and negative 1 half. Symmetrical? Oh shit, hold on. U1, V1, U3, and V3. And half, negative half, negative half, negative half, negative half, and half. Whew, damn. Finally, K3, right? So let's go ahead and do that one. Same EA over L, 280 times 10 to the 5th. So now we got, let's go ahead and do that. It's between nodes 1 and 4. So U1, V1, U4, V4. Same thing up top, U1, V1, U4, V4. All right. So plug in, we're gonna have cosine squared, sine squared, cosine squared, sine squared. So that is 1, 0, 1, 0, 1, 0, 1, 0. Then we have cosine, sine, negative cosine, sine, positive. So it's gonna be, it's 0 for all of them. 0, 0, 0. So that's a 0 up here too. Then negative cosine, negative sine squareds. You'll have -1 and 0. Symmetrical, so it's 0, -1, 0. This is 0, 0, and 0. Cool. Now we could go ahead and do the global equation, right? So step 3. Let's go ahead and do that. It's going to be a 8x8 matrix, right? We have 1, 2, 3, 4 nodes. Multiply by 2, x and y direction, so it's going to be 8. So you have, let me move it up, got f1x, f1y, f2x, f2y, f3x, f3y, f4x, f4y. All right. Again, they share the same EA over L, which is why we could add these matrices. Okay. They have the same common, whatever this thing's called, factor. It's not denominator, but you know what I mean. They all share the same 280 times 10 to the 5th. Close this one up here. So it's going to have U1, V1, U2, V2, U3, V3, U4, V4. Same up top, right? So you're going to have U1, V1, U2, V2, U3, V3, U4, V4. Close that up. And then finally, right, the displacement vector U1, let me go ahead and do this. Right, U1, V1, U2, V2, U3, V3, U4, V4. All right, cool. So before we start adding the whole matrix, right, let's go ahead and apply the boundary conditions first. And kind of, yeah, just so we can see what numbers are the most important. So U2 and V2 are fixed. U3 and V3 are fixed. Same thing with 4. So those 6 positions right here, U2, V2, U3, V3, U4, V4, they're all fixed. They all cancel out. They're all 0. So we can go ahead and just cross out the rows and the columns for U2, for node 3, 2, and 4. Okay, so let's go ahead and do that. So we're doing it. Just try to be as neat as you can because it's real easy to get lost. It doesn't hurt to be neat. Damn, all this is canceled out. All this. All right, cool. There we go. So that means we only care about 4 positions. This one, this one, this one, and this one. So cool. All right. Again, they cancel out here too. U2, V2, U3, V3, and the rows too. Just give me a second. Okay. Everything at node 4, 3, and 2, they all cancel out. We don't need it. It doesn't matter. It's not going to affect us. We could care less. We just don't care. Cool. So that means we only care about these positions. Okay, I'm going to cloud them up just real quick, just so you could see, make sure. I like to do it just so I can make sure I don't miss it, because sometimes it's not always just these like 4 connected positions. Sometimes it'll be like this one and this one, that one and that one. But I haven't came across it yet. I just remember that was the case for some problems. Maybe later on in some other chapters we'll see it, but for now, always do the clouds. I like it, right? So just add them. Add all the U1 U1s, U1 U1, U1 U1. So if you add that, you're gonna get 1.5, right? If you add all the U1 V1s, U1 V1s, 0, 0, and half, you're gonna get 0.5. Next one, half, 0, 0. So that's 0.5. Finally, it's half, 1, 0, 1.5. So cool. And we also know the force acting at node 1, right? So we could go ahead and replace these numbers right here. Let's go ahead and do that. So in the x direction, what do we got? We got negative 20,000. We want it in newtons, not kilonewtons, okay? Because this is in newtons, and that's gonna mess up your matrix. because this matrix is Newton per meter. This will be meter. Multiply them, you'll get a Newton. So you need to convert this here. 20,000 to the left. So it's a negative. Okay, negative 20,000. And then here we have negative 40,000. We're going down. So it's negative 40. Cool. That means we could go ahead and assemble the equations, right? So it's going to be negative 20 for the first equation. It's going to be negative 20,000 is equal to 280 times 10 to the 5th, parentheses, 1.5 times u1 plus 0.5 times v1. And for the next equation, it's going to be negative 40,000 is equal to 280 times 10 to the 5th, open parentheses, 0.5 u1 plus 1.5 v1, close parentheses. So let's go ahead and do that. My bad, I already have it ready, right? Just to save time. But do the equations, right? Just like I said, step 4 is negative 20,000 is equal to 280 times 10 to the 5th. What is that? 1.5 u1 plus 0.5 v1. I'm just writing down what I said earlier. And negative 40,000 is equal to 280 times 10 to the 5th. Don't forget this 280 times 10 to the 5th. Sometimes it's such a small little thing on your global equation that you'll easily look over it. But even if you forget it, I mean, once you get your answer, you should know something's up, because you're going to get like a high displacement if you don't do that. But, or a very low one or the other. It's usually like a 0.000, I mean, something like that, right? It's a small displacement. So, but you'll know something's off, right? It's like if it's extremely small, like 0.00000, right? It's like, you'll know you missed something here, just FYI. But, solve for the equations for u1, v1. You'll get negative 0.0007143 is equal to 1.5 u1 plus 0.5 v1. And for this one, you will get negative 0.00143 is equal to 0.5 u1 plus 1.5 v1. All right, so let me flip my paper. So this one's pretty easy, right? You just solve for one of these, u1 in terms of v1 or v1 in terms of u1, and then plug it into here. You'll be able to get it. So this one's pretty simple. But let's go ahead and continue that, right? So let's go ahead and move the first equation, 0.5 v1 to this side, and this one over here. Again, there's really no, you could have used this equation. You could have moved u1 over here, did that, but it doesn't really matter, right? Step 5. We will have, what is that? Negative 0.5 v1 is equal to, I'm using this equation, the first one, 1.5 u1 plus 0.0007143, and do the math, right? You will get v1 just divided by negative 0.5. You will get, what will we get? Negative 3 u1 minus 0.00143. That's not the answer, that's just a relationship. Now we're going to plug in this v1 into the second equation. If you plug that in, you will get negative 0.00143. What else is equal to 0.5 u1? I'm using this equation now. Plus 1.5 v1. Plug this in. Negative 3 u1 minus 0.00143. Cool. So if you do that, do the math, right? I'm gonna let you kind of figure it out, but if you multiply these two, that's negative 4.5 plus 0.5, that's negative 4 u1. So you will get, and if you move it this way and move this way, just pretty much do the math, right? 4 u1 is equal to negative 0.000713. That means u1 is equal to -1. -1.782 times 10 to the -4. And again, this is in meters. And then plug in this u1 into here. And you'll get v1 is equal to, what is this? -8.953 times 10 to the -4 meters. Cool. So we got this u1 and v1. Now we got to find the stresses. All right, just real quick before we do find the stresses, does this make sense? So u1 is going down, so x direction, x direction it's going negative, y direction it's going negative. So let's see. If we're pulling here to the left, then yeah, the x it's going to get displaced to a negative, right, negative x direction. And the y, if you're pulling down with 40, you're going to get like, assuming this pulls somewhat evenly, right, you're going to have like a displacement here. So is the original number, or original displacement, then when you apply these forces, you're going to kind of pull it this way, right? So yeah, it's a negative x direction, negative y direction. So yeah, that makes sense. It means we're on the right track. So all right, step 7 is finding the stresses. So this is the equation. The C minus matrix is this right here. So if you plug that in, right, let's do the first element. That's gonna be, what is it? So it's C minus, right? So C minus is this little matrix right here. E over L, that number is 210 times 10 to the 9 divided by 3. That's gonna be 70 times 10 to the 9, right? It is 70, right? 210 divided by 3, yeah, that's 70. Okay, so, and it's a negative cosine, negative sine, cosine, sine for the first element. So flip back, first element, 0 and 1. That's cosine and sine. These are the numbers we want. So 0 and 1, that is going to be, but they're negative. So it's 0, -1, then they're positive, 0, 1. Displacement vector, what is it? It's from nodes 1 to 3, remember? 1 to 2, remember? So that means we're going to have u1, v1. So u1 is -1.782 times 10 to the -4. And v1 is -8.953 times 10 to the -4. Then u2 and v2 are 0, right? They're fixed. Oh, cool. Let's go ahead and do the multiplication. We should get one solid answer, right? This is a 1 by 4 matrix. This right here is a 4 by 1. So that means when you multiply them, you will get a 1 by 1. That's it. So it's equal to 70 times 10 to the 9, right? Bringing this down. Open parentheses, 0 times the first number, which is 0, plus -1 times the second one. That is 8.953 times 10 to the -4, plus 0 times 0, plus 1 times 0. So cool. Just that number. Do the math. You will get 62.67, and it's in megapascals. Okay. This is 10 to the 6. So that's how I got this number. And since it's positive, this is in tension. So go ahead, block that in, make it look nice. Let's go to the next step. Well, not the next step, right? Just the next element. So next element, it's from nodes 1 to 3. And we care about radical 2 over 2 and radical 2 over 2, right? Cosine and sine. So same EA over L, right? All of them share the same one, same length, same modulus of elasticity. This is not parentheses yet. This is still a matrix. So it's going to be negative cosine, negative sine. That was negative radical 2 over 2. Negative radical 2 over 2. Positive radical 2 over 2. Positive radical 2 over 2. And then displacement, right? From U1, so I'm going to go ahead and -1.7 82 times 10 to the negative 4, negative 8.953 times 10 to the negative 4. We're going to move it up in case you can't see. And then U3 and V3 are 0. All right, so that means sigma 1, if you do the sigma 2, I'm sorry, is equal to 70 times 10 to the 9, parentheses, negative radical 2 over 2 times that. And it's going to be positive 1.26 times 10 to the negative 4. All right, plus, negative radical 2 over 2 times negative 8.953 times 10 to the negative 4. That's going to be a positive, what is that, 6.33 times 10 to the negative 4. And yeah, that's it, right? 0, 0. So do the math. I know I say that a lot, but just use your calculator. You will get 53.13 megapascals. And that is also in tension. All right. And don't worry, we'll kind of make sense of these numbers. I'll actually, the problem says just solve for the stresses, but I'm gonna go take it one step further in case you're curious. And I suggest you keep watching because the test is gonna most likely, he could ask for that, your professor or she, you know what I mean. Same E, right, for element 3. They're all the same length, same modulus of elasticity. It goes from 1 to 4. Your cosine and sine are 1 and 0. So the matrix is 1, 0, but it's negative 1, negative 0, or 0, and then positive, positive. Finally, it's right, it's from U1, V1. That's why it matters what angle you choose, because you got to make sure, if you had chosen the other angles, remember, like I said in the beginning of the video, you would have just flipped these. These two would have been down here, and these two would have been 0, because it would have been from the opposite nodes. Times 10 to the negative 4. U4 and V4 are 0. So cool. Let's keep it going, right? Sigma 3 is equal to 70 times 10 to the 9, open parentheses, negative 1 times this, 0 times that, 1 times 0, 0 times 0, so it's just this one we care about. That's positive 1.782 times 10 to the negative 4. Multiply that. Let me go ahead and move my eraser. Sigma 3 is equal to a positive 12.47 megapascals. And that is also in tension. Now, does that make sense? Yes, it does, right? Because they're all positive, meaning they're all in tension. Does that make sense? Yeah. If you're pulling with a resultant force, right? 40 squared plus 20 squared, it's going to give you something, right? Pythagorean theorem. This is your resultant vector. You're kind of stretching all three elements out. So yeah, it makes sense. They're all in tension. But let me go ahead and just verify. I'm going to show you how you would verify this. Like, verify force equilibrium at node 1. This is where they would ask for it. The problem doesn't ask for it. You could just cut it here, right? But I'm going to go ahead and show you how to do that, assuming they told you to find stresses. And now they want you to verify forces. So we know that, let me go ahead and put it right here, step 8. We know force is equal to sigma times area, right? Because sigma is equal to force over area. So let's go ahead and do that. So for the force 1, right here, sigma 1. So force 1 is equal to sigma 1 times area of 1. Now they all have the same area, but on the exam they might have different areas. You got to be careful. That's why I like putting 1 just to make sure. But 62.67 times 10 to the 6 newtons. This is Newton per meter squared, right? A Pascal. So 62.67 times 10 to the 6 Newton per meter squared times 4 times 10 to the negative 4 meters squared. You're going to get newtons if you multiply them. So it's just 4 times 62.67 times 100, right? Because it's 10 to the 6. is 10 to the negative 4, so it's just 100. So if you do that, your force 1 will be 25,068 newtons. And again, it's positive, so it's in tension. You'll see why we need that in a second. For force 2 is equal to sigma 2 times area of 2. That's going to be same thing, 53.13 10 to the 6 times 4 times 10 to the negative 4. If you do that, you will get 21,252 newtons, and that is also positive, so it's in tension. Finally, force 3 is going to be sigma 3 times area of 3. Area just so happens to be the same, so it's 12.47 times 10 to the 6 times 4 times 10 to the negative 4. You will get 4988 newtons, and that's also in tension. So that's how you would do this. This is how your diagram looks, right? You got 3 beams like this. There's a 45-degree angle. We got a negative 40,000. And we have a negative 20,000. Okay? When it's in tension, you're pointing away from the node. Okay, so all of them are pointing away. They're all in tension. If it was compression, you would have flipped the arrow. It would have been facing this way. Okay, just FYI. That's why this is important. Tension, tension, tension. Compression would have switched your signs, and if you didn't know that, it would have messed you up. But let's go ahead and continue, right? This one, force 1 is 25,068. Force 2 is 21,252. And then this one is 4988. So now it's easy, right? Just sum of the forces in the x direction. You don't set it equal to 0. They should be equal to 0, okay? I'm setting it equal to 0, but I'm saying they should be. That's how you know you did it right. We don't set it equal to 0. So let's go ahead and do it. Positive x, this one's positive 4988 plus, let's do this one, 21,252. But you want the cosine, 45. Minus 20,000. If you do that, I did the calculation. It's approximately equal to 0. I think the real answer was like 15. Okay, something like that. But yeah, that's just a rounding error. We're good. Some of the forces in the y should be equal to 0. That's not what it means. We're not setting it equal to 0. It's just should be. To the y now, it's positive 25,068 minus 40,000 and plus 21,252. Now we want the sine. We want the vertical component. So that's sine 45. And if you do that math, you will get also equal to 0. I think it was also equal to 95. And again, that's a good buffer, right? We're dealing with thousands of newtons. If we're off by 95, we're pretty much correct. So that's like just something you should be like, okay, I guess that makes sense. But yeah, that's how you would verify it. So it's really important, you know, assuming you have your stress values. If they tell you to go ahead and apply the local element forces like 327 did, and I guess that's easier, right? But assuming you only have stresses, that's how you would do it. But yeah, that's the answer. That's the top part. That's the bottom part, and then top part of the back, and then bottom part of the back.